Okay, what about a line or a curve? Use a matrix method to determine the image of the line y equals 2x minus 1 when reflected in the y-axis. Well, reflection in the y-axis, let's work out where things go. So we're reflecting in the y-axis. So 1, 0 ends up at negative 1, 0. And 0, 1 doesn't move. Okay, I have my transformation matrix. It's going to transform coordinates xy to coordinates x prime, y prime. But as always, when we're doing this kind of a problem, what I actually want to know is the opposite. I want to substitute something else for x and y into this equation. So I need to pre-multiply by the inverse of this matrix here. What's the determinant of this matrix? Negative 1 take 0, negative 1. Then I'm going to swap these around and change the sign of the 0, which doesn't make any difference. Oh, and when I multiply negative 1 by this matrix, I end up with the first matrix I started with. Of course that makes sense, doesn't it? If I'm reflecting in a line, actually let me go up to look at the previous diagram. If I'm reflecting across a line, what's the inverse transformation? It's going to be reflecting across the same line. So the inverse transformation for a reflection is going to be itself. That is the inverse. And you can prove it by working your way through. Year 12 students who've done your trig identities, have a go at trying to prove that the inverse of a general reflection matrix, you know, the one with cos and sine of 2 theta in it, have a go at proving that the inverse of that is itself. Anyway, here, what I've learnt is that x primed is equal to negative of x. There's a negative sign. And y primed is just equal to y. So I substitute those in to my original equation, y equals 2x minus 1, and I get y primed is negative 2x primed minus 1. Now that makes sense. If you think about the graph, here's y equals 2x minus 1. If I'm reflecting around the y-axis, I'm going to end up over here. Same crossover point at negative 1, but the gradient will be negative.